Have you ever just stopped and really thought about light? I mean, it's incredible. It zips from the sun to the earth in just over 8 minutes, and it's the only reason we can see, well, anything. So in this explainer, we're going to do something fun. We're going to follow the amazing journey of a single photon, all the way from its super mysterious origins to the exact moment it hits your eye, to really get a handle on the physics of optics. Right off the bat, we have to tackle the biggest, weirdest question of all. Is light a stream of tiny little particles, kind of like tiny bullets, or is it a wave rippling through space? Well, the absolutely bizarre and fascinating answer is, it's both, and that central mystery is exactly what we're going to unravel. So for the first leg of our photon's journey, we've got to understand this strange dual nature. It's a concept that, believe me, puzzled some of the greatest scientific minds for centuries. Yeah, our understanding of light has really been a wild ride. It all started with Isaac Newton, who figured light had to be made of tiny particles. He called it his corpuscular theory. But that didn't quite explain everything. Then, along came Christian Huygens, who showed that light also behaved like a wave, which could explain things Newton's theory couldn't. The debate raged on until James Clerk Maxwell came along and unified electricity and magnetism, proving that light is an electromagnetic wave. And finally, Albert Einstein and Max Planck blew everyone's minds with the quantum view, that light is made of these discrete packets of energy called photons, which have this crazy ability to act like a particle one moment and a wave the next. That's wave-particle duality, and it's right at the heart of all of modern physics. Okay, so let's break down that official definition. Light is a transverse electromagnetic wave. So transverse just means the wave vibrates at a right angle to the direction it's traveling. The easiest way to picture it is just shaking a rope up and down. The wave moves forward, but the rope itself moves up and down. And electromagnetic? That's the secret sauce. That's what lets light travel through the total vacuum of space. Unlike sound, which needs something like air or water to move through, light doesn't need any medium at all. And that's how our little photon can cross that vast empty void between the sun and the earth all on its own. So our photon has made this epic journey across space. What happens when it finally hits a surface it can't get through, like, say, a mirror? Well, it reflects. You know, the rule for how light reflects is just beautifully simple. It's called the law of reflection. And all it says is that the angle a light ray hits the surface, that's the angle of incidence, is exactly the same as the angle it bounces off, the angle of reflection. You'll notice that normal line in the diagram, that's just an imaginary line we draw at 90 degrees to the surface to measure from. It's this simple, predictable bounce that lets a totally flat or plane mirror create that perfect reversed image of you. Now, things get a lot more interesting when the mirror isn't flat. If you have a concave mirror, which curves inward like the inside of a spoon, it gathers up all the incoming light rays and focuses them down to a single point. We call this a real focus because the light rays actually meet there. But a convex mirror, which bulges outward, does the exact opposite. It takes the light rays and spreads them out, making them look like they're coming from a single point behind the mirror. And since the light isn't actually back there, we call that a virtual focus. Okay, I know this matrix looks a little intimidating, but the main takeaway is actually super simple. For a concave mirror, where you put an object completely changes the kind of image you get. So for example, if you place an object between points C and F, you get an image that's real, upside down, and bigger. But move that same object closer between F and the mirror, and suddenly the image is virtual, upright, and magnified. This is exactly how a makeup or shaving mirror works. When you get up close, you see a bigger, upright version of your face. It's all about where you are relative to that focal point. And these principles are at work literally all around us. A concave mirror's ability to focus light into a powerful, tight beam is perfect for a flashlight or a car headlight. And a convex mirror's ability to spread light out and give you a super wide field of view is exactly why they're used for the passenger side mirrors on cars or for those security mirrors you see in shops. So, reflection is what happens when light bounces off a surface. But what happens when our photon tries to pass through a substance, say, moving from the air into a glass of water? Well, it bends. I'm sure you've all seen this classic illusion, right? You stick a pencil in a glass of water, and it looks like it's broken right at the surface. This isn't just your mind playing tricks on you. It's a fundamental property of light itself. It's called refraction. And refraction happens for one very simple reason. Light changes speed. Our photon travels at its absolute fastest in a vacuum. But the second it enters something denser, like water or glass, it slows down.
And this sudden change in speed forces it to change direction. It makes it bend. That's why the light coming from the part of the pencil that's underwater travels a slightly different path to your eye, making the whole thing look broken.
Now, under just the right conditions, light won't even escape a substance. It gets trapped inside. This is called total internal reflection. And for it to happen, two things need to be true. First, the light has to be going from a denser medium to a less dense one, like from water out into the air. And second, it has to hit that boundary at a pretty shallow angle, an angle greater than something we call the critical angle. If it does that, instead of escaping, it just reflects right back into the water.
And this whole principle of trapping light is the magic behind some incredible stuff. The internet data you're probably using to watch this is flying through the country as pulses of light trapped inside optical fibers. That brilliant sparkle you see in a diamond, that's caused by light getting trapped and bouncing around inside all its little facets. Even a mirage you see on a hot road is caused by light bending and reflecting off a layer of hot air right near the ground.
So far, we've kind of been thinking about our photon as a single thing. But the white light we see from the sun isn't really one thing at all. It's actually a whole bundle of all the colors of the rainbow, all traveling together.
This has to be one of the most iconic images in all of physics, right? A prism splitting light into a rainbow. This phenomenon is called dispersion, and it happens because when light enters the glass, different colors actually slow down by slightly different amounts. Violet light, which has a shorter wavelength, gets bent the most, while red light, with its longer wavelength, bends the least. And that's what spreads all the colors out into that beautiful spectrum. This is the exact same thing that happens with rainbows, just with tiny water droplets in the air acting like millions of tiny little prisms.
A related idea called Rayleigh scattering is what answers that age-old question, why is the sky blue? See, as sunlight enters our atmosphere, the tiny molecules of nitrogen and oxygen start scattering the light. But they are way, way better at scattering the shorter wavelengths, like blue and violet light, than the longer ones. So that blue light gets scattered all over the place and comes at us from every direction, which paints the whole sky blue. Now, at sunset, the sun is on the horizon, so its light has to travel through way more atmosphere to get to you. By the time it reaches your eyes, most of the blue light has already been scattered away, leaving those longer direct wavelengths of red and orange to really dominate the view. So this brings up a great question. How do we even see the color of things? I mean, why is a rose red? It's not like it's making its own red light. What happens is when white sunlight, which contains all the colors, hits the rose, the pigments in the petals absorb most of those colors. They only reflect the red wavelengths. And it's those reflected red photons that travel to our eyes, telling our brain, hey, this is red. An object that looks black absorbs all the colors, and an object that looks white reflects them all. Simple as that. And that brings us to the final destination of our photon's long journey. After traveling 93 million miles, maybe reflecting off a mirror, bending through some water, and scattering off the atmosphere, it finally arrives at the one place where all these amazing principles of optics come together to create the miracle of vision, the human eye. The eye is just a remarkable biological camera. Light comes in through the cornea, then the pupil, and gets focused by this flexible natural lens. This lens refracts or bends the incoming light, aiming it perfectly onto a light-sensitive screen at the very back of the eye called the retina. The retina is covered in millions of photoreceptor cells that turn these photons into electrical signals, which then get zipped off to the brain to be interpreted as an image. For you to see clearly, that focus has to land exactly on the retina. But sometimes that focusing system isn't quite perfect. If you're nearsighted, the technical term is myopia, it means your eye's lens is focusing the light a little too soon, in front of the retina. This makes distant objects look blurry. To fix it, we use a concave lens, the same kind that spreads light out, to push that focal point back onto the retina. Farsightedness is the exact opposite problem. The light gets focused behind the retina. So here, we use a convex lens to bend the light a little more strongly and pull that focal point forward. It's a perfect real-world example of using these fundamental principles of optics to correct our own biology. And of course, we've taken these principles so much further. By combining lenses and mirrors in clever ways, we've built incredible instruments that extend our senses far beyond their natural limits. Telescopes use huge lenses or mirrors to gather up the faint light from distant stars, while microscopes use a similar combo of lenses to magnify the tiny, invisible world right under our noses. Both are just a testament to our incredible mastery over the journey of the photon. And that leaves us with one last thought to chew on. Everything we've talked about, from rainbows to red roses to the screen you're watching this on, exists in this one tiny, tiny little sliver of the full electromagnetic spectrum that we call visible light. Our eyes can't see radio waves or microwaves or X-rays, and it just makes you wonder, what incredible sights and phenomena are happening all around us right now in wavelengths our eyes simply never evolved to see? What wonders are we blind to?